Hello, everybody. Welcome to this seminar about good practice in finite element analysis, created and presented by Peter Debney and brought to you by CMB Engineer Competence Centers. My name is Jānis Berkis, and together with Jānis Šliseris, we will be responsible for moderating this event and helping Peter. Before I give the screen to Peter, I will share some key information about this seminar and your abilities to interact. So this is the program. Peter will go in more detail about this program today, but the seminar is split into 3 major sections with 2 30-minute breaks between each of them. This is the time when you can grab some coffee or have a lunch. And each of these major sections include 2 to 3 subsections, and after each of these, Peter will be able to answer your questions. So Jānis will read your questions and ask them to Peter. So let me give you information about how to ask these questions. So all your microphones are muted, and the only way to ask questions will be via the chat functionality, opened with the chat button on the bottom side. After you write that question in the chat box, you can do it on the right side. Jānis Šliseris will ask it to Peter at the designated times. So please also avoid using the reaction buttons, as this will have no effect on the question asking procedures. You can write your questions either in Latvian or English, and then Jānis will translate them into English if necessary. Jānis will also choose the most appropriate questions if there are too many, and if the time will allow, the rest of the questions will be asked to Peter at the end of the seminar. So there will be approximately 2 to 3 questions at each of these subsections. So as I mentioned, after the seminar, there will be a 30-minute questions and answer session where Peter will try to answer as much questions as possible from you. The final note, please write your full name in the participants list. You can press more and rename to do that. If you are listening more than one person from one computer, please write all the participants' names. This will be checked against the participants list in case it doesn't correspond, or you do not rename and leave, for example, some numbers in the names list. You will be kicked out. If anything happens with the seminar connection, use the same link to connect back. Thank you, and I'm giving the word to and the screen to Peter.
Great, thank you very much, Jānis. Okay, let me share my screen. Okay, you can see that now? Jānis?
Yes, okay. I think.
You're seeing the PowerPoint?
Yeah.
Okay, I'm going to start. So let me introduce myself. So my name is Peter Debney. I am a structural engineer. More than 30 years experience now. I'm chartered with the Institute of Structural Engineers, and I'm a fellow of that institution. I work for Arup, and in particular in the digital technology group, which is usually known as Oasis outside the company. So I've been working with finite element analysis and CAD and BIM and so on for many years. You might know one of my previous products, now known as Technostructural Designer, Technostructure. Many years ago, these days I work with finite element analysis programs such as GSA. And also, I've written a book on computational engineering, which will be published this month, which is very exciting. This is published by the Institution of Structural Engineers, and this covers all the topics we'll be looking at in today's session, but also a number of others, because we can't fit everything in to just one day. So this will be covering finite element analysis in all its versions, parametric design, optimization, AI, future of computing for engineers, and so on. And if you're interested in the copy, you can access it via the link, or search for computational engineering on the Institution of Structural Engineers website. So without further ado, let us get started. So finite element analysis. Now, finite element FEA, easy to say, or FEM, the finite element methods, has become the dominant engineering methods in the last few decades. And the reason for this is that it can analyze any structure with any material, just about, though some materials are more suitable than others. It allows us to analyze static analysis, but also dynamic, and the linear and non-linear problems. Now, the results, quality of the results, are dependent on the suitability and the quality of the software and the model and the analysis method chosen. So whilst the programs are very powerful, a lot of the responsibility is in your hands to make sure that you are producing good models which are appropriate for the question at hand. Now, finite element analysis covers many methods. Now, the main method that I'm sure people are aware of is the static linear analysis, as also known as the stiffness matrix. And I think many people could cover this at university, but I will give you a recap for those whose memories have lapsed a bit. But there's also P delta analysis, which is the stiffness matrix plus the geometric stiffness matrix, which basically says axial loads on elements can increase or decrease stiffness. Then there's buckling analysis, where we take the stiffness matrix plus the geometric stiffness matrix, and we look for those axial loads where the stiffness of the elements goes to 0. Now, in the P delta analysis, this will cause the analysis to fail, but we're actually looking directly for these in the buckling analysis, and we use an eigenvector or eigenvalue analysis to find these values. Similarly, there is the modal analysis, which, like buckling, uses eigenvectors, but then uses the stiffness matrix plus the mass matrix, and can optionally also include the geometric stiffness matrix. This will look for the natural frequencies of the structure that you can then use for vibration analysis. And then there are the non-linear analysis methods. There's the Newton-Raphson method, which is a multi-step P delta analysis. There's dynamic relaxation and explicit solvers, which do not have a matrix at all, but instead displace the structure until equilibrium is found. And then there are also meshless and particle methods, which don't use elements at all, just nodes which are free to move around. Now, today, for time and so on, we will just look at the static linear analysis methods. To cover all the methods would be possibly a whole day or more in itself. So the stiffness method itself. Basic concepts, first of all. First, that the whole structure is in equilibrium. Every node is in equilibrium, and every element is also in equilibrium. Now, if we were to get onto non-linear analyses, then these are able to deal with structures which are not in equilibrium. But yeah, the stiffness methods everything is in equilibrium, whether the whole structure or also the individual parts. Now, the force in an element, the axial loads and so on, equals the deflection times the stiffness. F equals Ku. This is the fundamental equation of the stiffness matter method. Now, we know the external forces and we know the element stiffnesses. It's the deflection that we need to find out. Now, at the beginning of analysis, when we first design the structure, we might not know all the section sizes, so we do need to make a guess. Unlike the simple hand calculations for beams and so on, where we do not need to know the stiffness of the elements, we do need to have a section size for a finite element analysis before we start. We might change it later, but we need to have a guess. Now, the external forces and element stiffness is known, so the deflection is unknown, so we need to rearrange that formula. So we have U equals F over K. The deflection is force divided by the stiffness. And we will write equations for every node in the structure. We will group these together into a matrix, and then we solve the matrix. So the force F, or the force vector matrix F, a vector being a matrix of just a single column. So the force vector equals the stiffness matrix times the deflection vector. Now, with matrices, we can't divide by a matrix. We can instead multiply by the inverse of a matrix. So the analysis will find the inverse of the stiffness matrix, multiply that to the force vector, and then give us the deflections. Now, a little bit more detail. So how does this work? So let's look at this simple structure, which is statically indeterminate, and we know that the node at the bottom will move, but we do not know how much it will move, but we will know it will move an amount, which we will call U. The distance moved will be a function of the force and the sum of all the stiffnesses in the elements. And we know that the node is in equilibrium, so the sum of the forces in the elements 1 to 6 is equal to the applied external force. Now, the strain of each element is a function of the element stiffness. So this is the Young's modulus times the cross-sectional area of the elements divided by the length of the element. Longer elements are less stiff, and the force itself. So if we sum up all these individual stiffnesses, the AE over L, that gives us the stiffness of the structure as a whole, with the F equals Ku again. So when we are applying this method in a computer program, there are 3 stages. There is the pre-processing, which is done by you. There is the processing, which is done by the computer, the program, and then the post-processing, which is then done by you, or usually within the same program, but possibly in separate programs. It depends on the finite analysis program that you're using. So first of all, the pre-processing, which is the model creation. You need to create the model. Now, the model is, maybe strictly speaking, a series of nodes connected by elements, but we normally think of it as being a series of elements which are connected at the nodal locations. We give properties to these elements, the section size, the materials, and so on. Maybe releases on the end of the elements if we're dealing with shear-only connections. There need to be constraints on the model. The constraints will always include restraints. Where are the support points? The boundary conditions, but there might be other constraints applied there. And then we need to apply the actions to the model. So these are forces that we apply from gravity and wind and so on. There might be moments, there might be external structures applying forces or moments to the structure, there might be thermal changes, there might be accelerations from earthquakes, and so on. And once we have this, we can then ask the program to process the model. So this is the solver. And what this will do is it will look at each individual elements, calculate the element stiffness matrices, and it will assemble these into a global stiffness matrix, which we call K, in the square brackets, which shows it's a square matrix. It then applies the boundary conditions by taking any line which has a restraint on it. We force the displacement to be 0. It removes those lines and the matching columns, and then inverts the matrix. Now, if we do not do that, then the matrix cannot be inverted. You cannot take a whole stiffness matrix and invert it. You have to remove the boundary conditions first, otherwise the analysis will fail. We then multiply the inverted stiffness matrix and the force matrices together, and that gives us the displacements. We then go back to the full stiffness matrix, and we multiply the stiffness matrix and the displacements to give us the reactions. This will also give us the applied external forces as well, which is a useful check on the calculations. And then finally, we then use the displacement matrix to find the strains in the elements, how much the lengths change, the stresses thereof, moments and forces, and so on, and all the other results that we then look at in the post-processing. Now, when post-processing on a linear analysis, we're able to multiply the results, combine the results to calculate the serviceability and ultimate limit state cases, so dead plus life or permanent plus variable, and so on. Now, this applies to linear analysis only. Non-linear analyses, we actually have to pre-combine these load cases in the pre-processing, but for linear analysis, we can do it afterwards. And then we might run design checks on the elements, so reinforcement calculations, section sizes, etc., output diagrams of results, numbers of results, reports, link through to other programs, etc., etc., etc. All right, so we're going to look in more detail at how this works. Now, for simplicity, we're only going to look at bar elements. Bar elements carry axial load only, and obviously there are other types of elements which work in essentially the same way. The maths is more complicated, the matrices are more complicated, but the principles are exactly the same. If you want to understand the principles, then the bar elements are a place to look. If you're interested in programming your own FE solver, then you will need to understand the other elements, and there are plenty of books out there, but today we'll just stick to bar elements, so keep things very simple. So, proof of the equation. First of all, stress on the bar is equal to the Young's modulus times the strain. Basic engineering. The stress is equal to the force on the bar divided by the cross-sectional area. Stress equals force over area. And the strain is the extension over length, U over L. Now, we can then substitute these equations into the first equation, and we have the force over area equals Young's modulus times U over L, and we can rearrange and take A over to the right-hand side, and so we have F equals AE over L times U, and then AE over L is the stiffness, and we call this K. F equals KU again. Now, if we have movement at both ends of the bar, then we can look at the forces at each end individually, and the the deflection is deflection on one end minus deflection on the other end. U1 minus U2 or U2 minus U1. And we can then compile these two equations, these simultaneous equations, into a matrix, as you can see here. So we have the force vector on the left, F1 and F2, and then stiffness matrix. Now I'll take an AE over L outside the matrix, just so you can see the matrix form itself, the 1 minus 1, etc., just for clarity. Within the program, that AE over L would be within the matrix itself, but that would complicate things a little bit on the screen. But the program itself, it's just looking at pure numbers in there, so we keep it all within the one matrix. And then there's the displacement matrix at the end, and we have the element stiffness matrix at the bottom, and we call this KE. This is the stiffness of the individual elements, not the overall stiffness matrix. To get the overall stiffness matrix, we combine the individual element stiffnesses together, and we can see in the matrix at the top, we have the stiffness matrix of element 1 at the top, the stiffness matrix of element 2 at the bottom, and in the middle they will overlap because they join at node 2, and you see displacement node 2 here and the force at node 2 here. You also note that the matrix is symmetrical about the diagonal, and it is sparse, that there are zeros in there. Now, for a full stiffness matrix, there will be a lot of zeros, and we'll have this central zone, which is also known as the bandwidth. You may have heard that mentioned. And the ordering of these gives us the narrowest bandwidth possible to give maximum efficiency. In the early days of finite element analysis, this bandwidth was your responsibility, and it was based on the nodal numbering. Today, modern programs will automatically take your node numbers and they'll internally shuffle them around to minimize this bandwidth to give us the most efficient, fastest analysis. And we can see that the equation, the matrix, multiplied out, and we see it's all ones apart from the 2 in the middle where they add together and zeros at the corners. Now, we now apply the boundary conditions. So we see that node 1, this is restrained, so its displacement will be 0. And also note, in this example, to keep things simple again, we're only considering movements in horizontal direction. So node 1, it has a 0 movements, so we know U1 is going to be equal to 0, so we can just strike this line out, and the stiffness matrix must remain square, so we'll also remove both the first row and the first column as well. This gives us the reduced stiffness matrix. Now, the advantage of this is that, as mentioned, this matrix cannot be inverted, this matrix can. Now, the inverse of a 2x2 matrix is this simple little formula where we swap over the top left and bottom right values and negate the other two values, and then divide everything by this value. 3x3 matrices a little bit more complicated, and so on. But all the inversion is based around this formula. Now, strictly speaking, for a full FE analysis in the computer, they tend not to use this method. It is possible, but there are actually faster methods of inverting a large amount of matrices. But let's just stick with this one for the time being. So the inverse of this stiffness matrix is this. So we have L over A1112 times the applied forces. We can multiply these out now, which gives us the displacement U2, and displacement at U3. And we can see they are both PL over AE or 2 PL over AE. So we can see immediately that the displacement at node 3 is going to be twice the displacement at node 2. This is good. This is what we should expect. Now, we substitute these displacements back into the original equation. And so we can see displacement 0 at node 1, PL over AE at node 2, and 2 PLA at node 3. Now, these AE over Ls will cancel out, leaving us with this equation at the bottom. And we can see the forces are, or displacements are 0, P, and 2P. Now, to calculate the forces at each node, we can multiply this out, and we can see that the force at node 1 equals minus P, which is a reaction, which is good. It's the equal opposite to the applied force. Node 2 completely cancels out. There is no net force at node 2, which is also good. It's an equilibrium. And node 3, we calculate it and we come up with the answer P, which was our original value. And that shows us the maths has worked. And there's been no loss of accuracy in this calculation. Larger calculations, you might find a slight difference in the final values, and that gives you a measure of the accuracy, or an measure of the accuracy. So now we have the displacements. We now calculate the forces in each of the elements. We do this from how much the nodes move relative to each other. So we can now calculate the strains in each element, which is the difference in the displacements at the ends. And that gives us the strain values. And then for those strains, we can then calculate the forces in each element. So if we look at the first element, we can see the force is AE times P over AE, which equals P. So the force in element 1 is P, and I'm sure you're not surprised, but I'll leave you to check it yourself, that the force in the second element is also P. Now that was a bar in 1 dimension. If we are looking at a bar in 2 dimensions, then you can see we now have our rather 2 by 2 matrix. We have a 4 by 4 matrix, and we see we now have a number of sines and cosines values based on the angle of the bar in 2-dimensional space. Similarly, if we were looking at a bar in 3 dimensions, then you'll be a 6 by 6 matrix. And rather looking at the displacements at node 1 in the x and y, and the x, y, and z direction, and node 2 x, y, and z direction, and so on. Now, because this matrix is quite complicated, a lot of values are repeated. You sometimes see a shortened version of this matrix, where say cos alpha equals c and sine alpha equals s, and we then get this shortened version, which is easier for us to read. And yeah, as I said, for beams, for shells, and all the other element types, the principles are exactly the same, only with bigger matrices and more complex formulas. So, for example, a beam matrix would have values for the rotation of the nodes, and so on. Now, so we often hear talk about degrees of freedom. So in this bar, as we see here, the bar itself has 1 degree of freedom, so it can extend or shorten, and so it only has axial load. The nodes, on the other hand, they have 2 degrees of freedom. They are free to move in the x direction or the y direction, and there's some combination of those. There is no consideration of nodal rotation in here at all. that there is no consideration of rotation, so rotation is not included in the calculation. It is completely ignored. If we are analysing a beam element, then there will be terms, degrees of freedom, for the rotation of the nodes, and likewise bending of the beam elements, shear in the beam elements, and so on. Okay, so the analysis said that there are some assumptions and simplifications in this analysis to make it simple. So, first of all, assumptions within a linear analysis. We assume that the deflections are small. The structure is not going to move very much. In fact, for most structures, you won't even see the displacement. You might be able to measure it carefully, but in general rules, you will not see the movement of the structure. Because the deflections are small, we are finding the equilibrium at the original undeflected position. There is a linear relationship between loads, deflections, stresses, and strains. And because of this, we can then factor combinations are multiples of the original results. So we can analyze permanent loads separately to the variable loads and so on, and then add them together afterwards. Now, these are our assumptions in the linear analysis. If we look at non-linear analysis, we can have large deflections. The equilibrium is found at the deflected position, not at the original position. So we need to find that deflected position first before we can calculate the forces, which is difficult. There's likely to be a non-linear relationship between the loads, deflections, stresses, and strains, which means that the analysis must use factored load combinations. So if we look at this structure on the right-hand side, we can see there is a vertical force, a horizontal force, and there is some stiffness in the elements. Now, the force F will push the node 2 to the right. The force P will pull the node 2 to the left until it reaches zero displacement, and both are controlled by the stiffness. Now, the actual displacement of that node is down to a combination of P and F. Now, if we apply just P, then displacement will always be zero. The force F would induce a deflection, which will be a factor of the load K and the load P. So we actually have a non-linear relationship here, looking at displacement for node 2. We cannot analyze node P and node F separately. That this is a non-linear problem we are looking at here. Now, similarly, we can reverse that load, so the structure might buckle. So a linear analysis can produce forces that the structure just cannot carry. The real structure might buckle, it might yield, it might break, and so on. And so generally for a linear analysis, we need to then run separate checks to make sure that the structure as a whole is actually strong enough to carry the applied loads. And here we have three sections at the bottom, cruciform I section and box section. These all have the same cross-sectional area, but you can notice they will have very different bending capacities and very different buckling capacities. So if we were looking at just the element area itself, yeah, this would not inform the buckling analysis correctly. So we need to understand the various other properties of the sections. Other analysis assumptions and simplifications. All computers will round the numbers. Now, a real structure deals with real numbers. Well, it deals with the real structure. It deals with real physics, which we represent as numbers. And any number in a computer is an approximation. It represents a range of values, and the real number can be somewhere within that range. So if we look at the top graph, we can see a series of integers, 1, 2, 3, and so on. And each integer, for example, number 1, represents a range of values from half to 1.5. Number 2 represents from 1.5 to 2.5. So we can say quite truthfully that 1 plus 1 equals 3 for some large values of 1. Similarly, floating point numbers also represent a range of numbers, and if we look at the floating point value, you see each value represents a larger and larger range as we move, as the numbers grow. Now, in this instance, I've just looked at a single significant figure. Computers obviously deal with many more, but the principle remains. Floating point numbers represent a range of numbers. This also means that for maximum accuracy in your FE analysis, your model coordinates should be as small as possible. So in general, the model origin, the 0, 0, 0 point, should be somewhere close to the model, possibly within the model. I would advise seeing if you can find a point in the model, at least on plan, within the structure, maybe one corner, maybe the middle, to make that the 0 point. The elevation, the Z direction, yeah, use the structural elevation for that. It's not normally that big. Or you might use a site coordinates, that the 0 point is within maybe tens of meters of the structure. This will be fine. What you do not want to do is to use national or international coordinate positions for the structure. Now, the CAD programs, the BIM programs, they might require that to give you to ensure the models overlap with each other when you share with the architect and so on. But the analysis model, you need to make sure the 0 point is close in or within the model itself to give you the best, most accurate results. Other analyses, assumptions. So the model cannot totally represent reality. It's a model. It's a bit like when we make plastic models of airplanes and so on. It's not the real thing. It is a simplification. It is a reduction in detail. Also, yeah, things like dimensions. They're approximate and probable. We are specifying the dimensions of a structure which has not yet been built. Or alternatively, we might be analysing an existing structure where we have gone and measured the dimensions to the best of our ability. The material properties are approximate and probable. We may specify the concrete grade and the steel grade, and the manufacturers will provide materials which are usually stronger than that, not always, and probably stiffer, perhaps, or not, but somewhere around about there. And the loading is approximate and probable. We don't know for certain how much snow will fall over the next 50 years. We don't know for certain how much wind will blow over the next 50 years or more if we're designing a bridge. We have good approximations of what will probably happen. And one of the arts of engineering is to make suitable simplifications. Now, As a graduate, you're first starting off, you don't have much understanding. You've got some, but the understanding is growing, and your models will tend to be quite complicated because you're still learning. As you grow in experience, the models you make will get simpler. You're able to produce the same results from simpler models, and you realize that handrailing, I don't need it. Some other models, oh, I can leave out this structure, or I can leave out that, and so on. And you can get the answers you need from simpler models. This takes practice. So stick with it. And you can see, for example, at the bottom, 3 different supports. The analysis support on the left, it's just a pin. But the reality is it could be a bearing, it could be a bolted connection, and so on. And in general, we don't need to model the connections in detail for the overall structure. But we might sometimes need to model the connections in detail in a separate model. Other assumptions we make, which is illustrated by the stool paradox. So here we have a simple wooden stool, and you sit on the stool. So how much load is in each leg of the stool? Now, if the stool has 3 legs, then you can be pretty sure that the load in each leg is 1/3 of the weight of the person sat on the stool. Now, if the stool has 4 legs, on the other hand, you think maybe each leg will carry 1/4 of the load, but that's not true. Actually, 2 of the legs will be carrying half the load each, but we don't know which pair of legs. So adding an extra structure, an extra leg on the stool has actually increased the load on those legs. The reason for this is the floor that the stool is sat on is not completely flat. The stool itself is not built perfectly. There is always some variation, and the result will be that you will have one leg which won't be in contact with the floor. The opposite leg will have maybe a little bit of loading, but not much, and almost all the load will be carried on just 2 legs. Now, this also assumes that the stool is very stiff. Wooden stools made with old-fashioned methods, they always have some flexibility in the joints, and they will flex and so redistribute the load. So the load is then redistributed equally between the 4 legs. A more modern stool with much stiffer glued connections, the stool paradox might still prove correct, and likewise you might overload the connections in the stool and break the chair. Okay, and at that point, I'll say, Yanis, are there any questions so far?
Okay, hello everyone. So my name is Jānis Šuiceris, and I'm a structural engineer from PECO group, and I will help to ask the questions. And at the moment, seems that in the chat there is no questions written.
Okay.
Yes. So maybe please write then some questions, and yeah, I can ask some questions myself until others will write some questions. So so you were speaking about displacement-based finite element method, and mainly about linear elastic method. As maybe you can give some comments why this exactly displacement-based finite element method has become so popular and not, for example, force-based finite element method.
I mean, the reason for that is because it works for the majority of our structures. The majority of our structures do work in the linear zone. There might be a small amount of non-linearity and so on, but usually for the majority of structures, the difference between a linear analysis and a non-linear analysis is very small. And a non-linear analysis will always take longer than a linear. And so if the answers are close enough and it's quicker, we use the static linear analysis methods. It works. Now, there are some structures where this is not the case, and so then in some occasions we will need to move over to a non-linear analysis, and we'll look at some of those later. So we look at these sort of long span bridges, stadium roofs, cables, fabrics, elements which are purely in tension or purely in compression, or maybe we're dealing with steelwork which is starting to yield, or reinforcements which is yielding, and so on, but still stable. In these situations, we might need to look at a non-linear analysis. But in the main, it works. It's simple. It's quick. It's good. It's good enough.
Mm-hmm. Yeah, I just wanted to admit, I think there is one big problem with non-linear analysis, that sometimes the result is dependent on load history, and in real structures, it's sometimes very tricky to add load history, which should be added there. So
very true. Yeah, it is difficult, and certainly if you're dealing with, say, very tall buildings, for example, you need to look at the construction sequencing, and so you get differential load column shortening and so on. And it is difficult, and we never know for certain, which is another reason for factors of safety, and not maybe putting too much detail in because we don't know the full detail. So we have to take a broad brush sometimes on the problems, but there are times also when that detail is very important. At that point, we do need to look very carefully at exactly what is going on and make our best estimations of the sequencing, the load history, and so on. And yeah, these are more difficult engineering problems. And yeah, and the engineers are sort of rewarded accordingly for dealing with those difficult situations.
Mm-hmm. Okay, I see that there is one question regarding the nonlinear analysis for precast concrete buildings. So in which case we should use nonlinear analysis for precast concrete buildings? Your opinion on it?
So for precast, a lot of it depends on exactly what you're trying to analyze. If you're looking at the bending moments and shear forces and so on, the linear and non-linear might not give much difference. If you're looking at the deflections of the elements when the reinforcement starts to yield, or maybe yielding at the connections, that would need a non-linear analysis. If you're looking at accidental damage, for example, the structure might be linear under normal situations, but let's say there is an accident. Let's say a lorry crashes into the building and breaks one of the columns, or there's a gas explosion or something like this. A column is gone, and suddenly the structure has to redistribute. It changes from a linear to a non-linear structure. The column above is no longer carried. It will drop down until the beams angle. So you start with the beams like this, and the beams will angle down, and rather than taking things and bending, they're then going to tension like a tie, and then carry the load to the random structure. This is a non-linear problem, and so that is a situation where I'd use a non-linear analysis on a precast. Indeed, any structure. Oh, yes, you're muted. Yanis, are you?
I suppose we can continue with the presentation.
Yes. Yeah. Okay.
Thanks.
Okay. Nice. Thank you. So, any other questions? Keep putting them into the chat box, and if we don't get them into these short sessions, we'll answer them right at the end.
So there is one additional question I will ask quickly then. If can we trust the finite element results for a complex structure buckling analysis? So is finite element results trustable in that case? What do you think?
It is trustable if you build the model correctly and if you use the correct analysis. Yeah, it might be, but the onus is on you to make sure that it is trustworthy, and we'll look shortly at how to validate and verify your models. So we will come back to that very shortly.
Okay, I think then this 5 minutes is gone, and we should continue with the lecture. There are a few other questions that I will try to ask later when we come.
Okay, so we'll start off about trust and so on. Let's see how you might avoid common mistakes in model. I mean, this is not an exhaustive list. I'm sure with practice you can create mistakes which I won't cover, but yeah, mistakes come with practice as well. So common mistakes. Firstly, if you are used to dealing, no, I don't know if the sound's coming through, sounds important, but anyway, if you're used to dealing with models in 2 dimensions, they might work. Turn that model into a 3rd dimension, and you might find the structure is unstable. 2-dimensional analyses always have an outer plane restraint. 3-dimensional analyses do not, and you need to make sure that those restraints are there explicitly in the model. Now, in this case, there should have been some roof bracing. The peak, if I just rewind back to the beginning, you can see that the top point, the peak of this portal frame, had no lateral restraints. Apart from they're all connected together by the purlins. A portal frame, I would normally expect there to be some cross bracing at one end, which will then stabilize the structure and carry these stability forces and wind forces and so on to one end and then down a braced bay. Don't do this. Here's another example. You may have come across the Hartford Civic Centre. If not, look it up. So this is a structural collapse which occurred back in 1978. So a very early use of finite element analysis for structures. It had been designed and built approximately 4 years earlier, and was one of the very first FE analyses of structures. In fact, because of the complexity of the space frame roof, the consultants managed to negotiate an additional fee for the computer analysis. Now, what then happened was that it was winter, snow fell, but only about half the design load of the roof, but the structure then collapsed. Luckily, the stadium was empty at the time. It was the early hours of the morning, but there had been 14,000 people in there just a few hours earlier. and if the snow had fallen then, well, I'm sure you can guess. The problem here was torsional buckling of the roof members. Now, showed the diagram earlier of the cruciform sections. This is looking at section here. So you can see all the structural elements in this building were made of 4 angles bolted back to back. So these sections had very little torsional capacity, and the design did not even expect torsion. And the analysis was purely a static linear analysis. So again, static linear analysis did not consider torsion. It's just not part of the analysis. And then the detailing of the structure, as you can see, it was designed with everything noded out as you expect for the truss, but as built, because it needed to be built with plates in between the angles, these connections then added torsion into the structure, which it just wasn't capable of carrying. Now, there were warning signs during the construction and erection of the roof. The steel fabricator found that it was very difficult to make things join up. They calculated the dimensions, but it was struggling to work. They struggled to get the cladding on. They found the roof was deflecting twice as much as they'd expected, as the engineering calculation predicted. Now, the engineer said the analyses are approximate, and you'll expect some difference between the calculations and reality, but not a factor of 2, not that much difference. And as you see, with so many of these structural disasters, there were warning signs, but they were ignored or they were dismissed. We've seen this again, the recent Florida University bridge collapse. There were warnings, but the people involved said it's fine, don't worry about it. And then other people suffer and die as a result. Let's avoid this. So torsion, often forgotten about. Now, some structures will generate torsion, and you need to check for it. Now, this is a model which I built following reading a case study of a project in London, where there was a masonry building being built on concrete beams, supported on piles because it's soft ground, and the engineer in question did use a finite element analysis program, used it to calculate and extracted out all the bending moments and shear forces from the structure and designed the reinforcements based on those. But during construction, as they were building the masonry onto the beams, so thankfully reasonably slowly, the beams began to fail, and then Arup was called in as a forensic engineer to find out what happens. And it turns out some of the beams had failed in torsion. Now, there was a clue in the model. I mean, obviously, this is not the real model. This is my model, but you can see in this model here, there is a bending moment at the end of one beam, but there is no bending moment in the other. And so the question is, where has that bending moment gone? And that bending moment has gone into torsion in the second beam. Every point is in equilibrium, and nothing is destroyed. So the moment, that bending moment became a torsion moment, which was not designed for, which was not detailed for, and so the structure fails. Luckily, no one was hurt in that case. Another case of making errors is mesh sizing. Now, this is the Schleppner oil rig disaster from 1991. And this was a gravity-based structure built in Norway. And you can see in the top right-hand corner here is a picture of their finite element analysis model of the gravity base. Now, they knew it was symmetrical, and so they were able to model just 1/4 of the structure and then put suitable boundary conditions on the cut lines. And for overall behavior analysis of the structure, this is not bad. As long as you're dealing with vertical loads and symmetrical loads. Obviously for horizontal loads and so on, not so good, but for vertical loads and water pressure loads, fine. Now, so this was good for overall behavior, but it was terrible for the detailed behavior. In between, so the structure consisted of these hollow tanks, which were initially filled with air, so the gravity base will float. So it's built in Norway, in the shipyard, floated out into the fjords. They then partially filled these tanks with water to give it ballast. And so the idea was it was float lower in the water, be more stable, and then tow it out of the North Sea, fill it some more, it would drop to the seabed, and they'll then build the top structure. Problem was, whilst they were filling the tanks with water for ballast, they suddenly heard some very loud bangs and realized that everything was going horribly wrong, and they were able to evacuate everybody in time before the base basically imploded, hit the bottom of the fjord, which was recorded on the seismic, the earthquake monitoring systems. So 3 on the Richter scale, which is a heck of a bang. And the end result was the structure was completely destroyed. It was just rubble. And what happened was that they had underestimated the shear forces in the structure. So if we look, so this is a model, it's a view of their model at the connection between some of these what they call tri-cells, these triangular areas in between the tanks, which has water on one side and air on the other. And so as you can see, it's designed to deal with nearly 100 meters head of water. So yeah, phenomenal pressures involved. This finite element analysis detailing, so this model was all 3D brick elements. The detail in these areas is not enough. The calculations are done at the nodal points, and the stress calculation from this simple mesh gave the stresses at about 50% of what they actually were. Now, a very quick hand calculation would have told them what the shear forces would be. 1 line, 2 lines of calculations on a piece of paper would have told them the shear forces were much lower than they should have been, and I mean, the structure cost $180 million US in 1991 prices. The cost today into the billions. For the sake of a simple calculation. Now, so the mesh size, what difference does it make to the calculation? So here again, this is my reconstruction of the model, just using 2D, and then calculating the stresses in the structure. And we see with the first one on the left, with large elements as they had, that there is measuring a certain amount of stress. But as we make the elements smaller and smaller, you see the stress values increase. and you can see the stress values, so the contours are the same on each of them, but you can see the stresses in these areas in the corners are gradually getting higher and higher. Now, there is a warning here. This is a sharp angle. Where we naturally get a stress concentration, and you will find that the smaller you make the elements, the larger the stresses will grow. And if you had infinitely small elements, then the stresses will become infinitely large, which of course is nonsense. There is some limiting point. Now, reality is there will be some cracking and release of the stress, and then it will be taken up with the reinforcements, which will then perhaps yield and so on. Yes, this is a risk you have of making elements too small. You overcalculate the stresses. Now, I say the reinforcement will take up stress, but unfortunately, the reinforcement detailing was also terrible. Now, normally you would have this bar would extend all the way across and up the other side. They went, we don't need to do that. The stresses are in this corner. We just have the bar extend a little bit further over, put the T head on the bar so it has a little bit of anchorage. That will be fine. Now, in tests afterwards, when they investigated exactly what happened, they found that the shear stress, the shear fracture, then went straight around the end of these T-heads and then broke the concrete walls. Now, were there warnings? Yes, there were. Previous design, very similar design, for a similar oil rig, also had major cracking in these same locations, but it didn't collapse. And so the engineer said, it's fine, it's worked before, we'll carry on. This time, not so lucky. Good design, good detailing, good analysis would have saved a lot of money. Thankfully, no lives this time, but a lot of money and reputation and so on. Other mistakes. Mesh discontinuities. There are times when you need large elements and small elements, and every node in a mesh, in a continuum, so the 2D elements, 3D elements, must be completely surrounded by elements apart from the edges. So here we have small elements at the ends, large elements in the middle. On the left-hand side, a bad connection. These nodes here, they're connected to the left, but not to the right. This is not good. On the right-hand side, we have a good continuity. So we go from small to large via some triangular elements or something like that. So it's a good transition. On the right-hand side, this is good. On the left-hand side, this is bad. Similarly, if we are mixing linear and quadratic elements, quad 4s, quad 8s, generally you'll be told don't do this, but in your judgment, you might go, he's probably all right. But you'll note that this node in the middle is connected to the element on the right, not to the left. This area here, this will give bad results. The calculation on the left-hand side for this element, the calculation of this element will be completely different. And yeah, the results will be unreliable. Another singularity, but like the stress concentration, is that some 2D elements do not have the full set of degrees of freedom. So here we have quad 8 elements, quadratic elements, and these do not have the full 6 degrees of freedom. They have only 5. So they have all the degrees of freedom apart from the local drilling stiffness. So these nodes are protected against rotation in all other directions apart from around the local z-axis. Now, in this case, we have a column with a pin base. This column is now torsionally unstable, and this will either cause the analysis to fail or if it does run, it will give you low accuracy results. Connections. Things should be connected. Now, in this image, I've graphically shrunk all the elements. Some programs have an option to just shrink things a bit so you can see the end node clearer, and you'll see there are two secondary beams, which are not connected to the primary. When everything's full length, it's not easy to see. With shrunk, you can see that the two beams are disconnected at one end. Elements have to share nodes to be connected. And this, again, will, if it's static analysis, the analysis will probably report an error. If it's a non-linear analysis, it might still work, depending on analysis methods, but you'll get some very, very large rotations and deflections on those beams. So watch out. This is a classic error. Make sure things are properly connected. Another popular error: getting the units wrong. We're putting numbers into the model to represent dimensions and forces and so on. But what do those numbers actually mean? Are they meters or millimeters? Are they newtons or kilonewtons? If you're not paying attention, your numbers can be out by a factor of 1,000. And of course, if you look at moments, you're multiplying forces and lengths together, the values could be out by a factor of 1,000,000 or more. Now, obviously, numbers which are so wrong are quite easy to check for. You look at the deflections. Is it deflecting millimeters or microns or kilometers? If it's microns or kilometers, you know something's wrong. Look at the solids display. The previous model, we showed the section sizes. I was asked, I said, problem model came in and said, when I switch on the solids, the model disappears. What's going on? And discovered that the model, they thought the model was in meters. It was actually millimeters. And so it was 1,000 times smaller than they were expecting, but the section sizes were still the same size, which meant that when we switched on the solids, everything vanished because the outer surfaces of all the elements were off the screen. We were suddenly deep inside the model. You could see the model if you zoomed out far enough, but that was the reason. And also, check total loads. Look at the total loads on the structure, the reactions you're getting out. It is always a good idea when you're running analysis to do a quick sum, estimate how much loads on the structure. You know about how much concrete, you know about what the plan area, and you know what the live loads are. You can do a quick calculation to say these are the reactions, the total reactions that I'm expecting, and you then compare those to the actually calculated in the software and see if they are close enough. They won't be exact, because that's why you're using an FE analysis to calculate things in detail. But they should be close enough. Otherwise, you know you've made an error. Another problem: offsets. So finite element analysis is not computer-aided design. Your CAD model is there to represent the physical reality of the structure. These are the detailed designs, so it can be built. So the CAD model has to have the exact correct levels. All the beams should have the same top level, and so on. Everything has to be in exactly the right place so that the people on site can build it. So that's so CAD is the physical reality, whereas the FE model should represent the physical behavior of the structure. So we need to make sure it's strong and stiff enough. So it's a common mistake, especially early on, to put all the top surfaces of the beams aligning so that the FE model looks like the CAD model. The problem with this is that it will give you strange results. It will give you unexpected forces and moments in the structure that you might not be expecting. So why is this? So here we have two simply supported beams, pin ends on both, and if you're paying attention, notice I do have pins at both ends and not a roller at one end. We'll come back to that. And you see one has been offset so that the top surface of the beam will line up with the nodes. So it looks right. But when we look at the bending moments on the two beams, we'll see they are quite different. The one at the top is working as we'd expect. We've got a bending moment which goes to 0 at the ends, and there's a vertical reaction. The beam below has bending moments at the ends. We're getting continuity which we were not expecting, and there's also large horizontal reactions, and there will be an axial force in that beam to match. Now, alternatively, if we had provided a roller support at one end, we would find the bending moments and reactions would be as we'd expect, but would also get a significant horizontal displacement at the end of the beam. Now, there are times when you do want to use the offsets like this, and we'll come back to that. But the basic problem is that the FE analysis assumes that the beams are modeled around the centroids of the structure, and if we offset to one surface, then we're suddenly working not at the neutral axis, and obviously with a beam, as it bends, the top surface shrinks, the bottom surface grows. And if we model to the wrong point, we will be picking up those behaviors and so on. So you need to be sure. There are times when you need these offsets, but only do it if you really, really want it. There are times when you will, and we'll come back to that. Confusion of releases and restraints. Now, they both begin with R. They both might be described as pins. But in the case on the left, we have pinned releases. There are releases at the end of the beams to represent connections, and so we'll get bending moments going to 0 and then axial loads in the columns. If you put pinned restraints at the ends of all the beams, you'll get 0 load in the columns, but you will get end bending moments. Don't make this simple mistake. I have seen it a few times. So boundary conditions. So here we have two trusses which are identical, apart from one has a pin at both ends, one has a roller support at one. So what difference does that make? So you can see that the top model has pins at both ends, and we're getting quite significant horizontal reactions at the supports, and the forces in the truss, well, it's not really a truss, it's an arch. The structure on the lower side, it is acting as a truss. We're getting equal compression tension in top and bottom booms, and we're getting vertical reactions only. Now, this is exactly the same as the offset problem we looked at just a couple of slides ago. This structure is supported not centroid, but on one side, which is what we expect from a truss. And not releasing at one end does induce these strange forces, same as the offsets. Now, in case of the truss, we do release at one end, we will get a horizontal movement, and this is to be expected. So watch out for your support conditions. Another support condition error. Now, this is one that I made. as a young graduate, I was tasked with analysing a water reservoir. So it was concrete base, concrete walls, contained water up to about here-ish, and I knew from modelling frames that I just put pin supports wherever there was a connection with the ground. Steel frames, that worked fine. But this structure, this gave me some unexpected results. Now, I had some idea of results I was expecting, and the bending moment in the wall part, that was fine. But the bending moment in the base was completely unexpected. And likewise, there was reactions, top and bottom of the thing. It was crazy. So I realized it's ground. I will put in spring stiffeners instead. And putting in spring stiffeners, suddenly the bending moment in the base then gave the bending moment that I was expecting. So when you're dealing with continuous structures, the support stiffness will make a big difference to, or can make a big difference to the results above. Now, this was putting in a calculated spring stiffness, but you can take it one stage further and model the ground itself and use the soil structure interaction. Is it worth the effort? In this instance, probably not. You might notice the bending moments are a little bit different, so maybe it should. Other structures where you're dealing with rafts and varying loads and varying ground conditions and so on, raft analysis, especially with moment frames and so on. Yeah, there are times when you need to look at soil structure interaction to give you appropriate results. So this support stiffness, it can change the moment distribution. So here we have a two-span beam continuing in the middle, just as we calculated at a university, and we get the hogging and sagging bending moments. But we put spring supports in there instead, and suddenly the results can be very different. Now, in the lower image, I've got quite soft springs. A real structure, the springs will be hopefully stiffer, but you will find if you put support springs under this in this analysis, you will get moment redistribution from the hogging to the sagging, and you see with enough softness in the springs, you will then actually get effectively two simply supported beams. And so, yeah, so you then look at the situation where you look at ground, soil structure interaction of the structure. And if you look at a large structure, you will find that the ground is effectively less stiff under the middle than it is at the edges. The soil stiffness itself might be consistent across the site, but the effective stiffness, due to the bulb action of the soil, the stress bulb, means you get more deflection in the middle than the edges, and so you get more effective stiffness at the edges than the middle. And this will, as you can see, redistribute forces and moments, shears throughout the structure. Right, lack of restraints. I'm just looking at the time. The model must be restrained in all 6 directions. 3 translation, 3 rotations. All nodes must be restrained in all 6 directions. And some analysis types will add restraints, like if you're doing a 2D analysis, I'll add restraints in. Now, if you don't have all these restraints on, then the model will want to shoot off to infinity, or in the case of international space station, it's in a dynamic equilibrium, not a static equilibrium. It is flying. Don't do this for your buildings. So 2D analyses, you're modeling a truss. The truss model at the top is a 2D truss in a 2D analysis. It's stable. Analyze the same structure in a 3D analysis, it's unstable. The upper model had restraints automatically in the y direction. Here, the lack of y restraints will mean zero stiffness, failure of the analysis model. Now, when in the Harvard Civic Center, they were assuming a lateral restraint from, and they used bar elements everywhere. And if we look at most of the points within the structure, yes, there is lateral restraint on all these points. But we look at the edge, these points here, for example, are actually unrestrained horizontally if we use bar elements. In these situations, we need to use beam elements, which do have moment continuity, but then releases at the ends. And something to watch out for. You can use bars in 2D, but quite often you need to use beam elements in 3D for trusses. And I'm thinking we've got yes, we've got just a couple minutes for questions, and I think that's a little bit behind schedule. Yanis, do we have any questions so far?
So far, we have left 2 questions from the previous questionnaire, but they are very related to the reinforced concrete slab design, and I think we should ask after your presentation about reinforced concrete design.
Okay.
But about this this part, I think there is no question at the moment. Yes. Yeah. So maybe I can one very small question ask. For me, it's very easy to imagine when the mesh size is too big for the structure, but it's less obvious when it's too small. Maybe,
yes.
maybe you can give some comments about that. And also, I didn't hear anything about integration points in finite elements, because sometimes you can get much better results with a coarse mesh, but just use more integration points. And yeah.
Exactly, yeah. So so element size, first of all, a general rule, a rule of thumb for element size is that so for 2-dimensional elements, the theory is that they are much wider than they are thick. So a good rule of thumb is the minimum width of a 2D element should be at least twice its thickness. So if you've got a 300 thick slab, the elements must be 600 by 600 as a minimum. When they start to get smaller than that, then we're getting into sort of deep beam territory, and the results are less accurate. So this also means that when you're looking at a slab, like a flat slab or so on, you can say, well, there's not much point reducing the elements smaller than ½ meter or so, because that won't give us. You might get some higher results, but these results aren't necessarily accurate. But it also means there's a lot of little details like little penetrations and so on that you can leave out of the analysis model, and so avoid these sort of false peak values. Integration points, yes. So as a general rule, most modern programs, if you're looking at quad 4, will have four nodes, one each corner, and so 4 calculations, but also they often do 1 in the middle, additional integration points, and then calculate the middle results and the corner results, and then to get together. A quad 8 will have 8 nodes around the edge and a middle point, and maybe 4 additional calculation points, integration points, or Gauss points within the elements. So a quad 4 might be doing 5 calculations. A quad 8 might be doing 13 calculations, and so give you sort of the better results for a similar element size. But quad 8s often do not have the drilling degree of freedom, so that's something to watch out for.
Okay, actually we have now time for the break, but there is one question. So this question, I will ask, actually 2 questions. So this I will ask then at the end.
Okay.
Mhm.
All right. So so we'll take a half-hour break at this point, and we're back at 12 to look at validation and verification of your model.